Anyway, I'm Gilberto Thomas from Brazil. I am a long-term collaboration of James since the beginning of this project, CompuCell3D project, since the time it was CompuCell2D actually. And today I'm going to show you these features of CompuCell that allows you to implement and understand cell properties and behaviors which determine the cell shapes in the simulations. Let's start with begin with the topics here. I will show you about the motivation of this talk, the cell shapes themselves, and then I will go over a few exercises to show how to implement the cell shapes in the simulations. This is going to be done with some plugins, the volume constraint, the surface constraint, and the length constraint. Okay, we are going to do exercise for each one of these topics here. Okay? So to start, let's talk a little bit about the cell shapes. There is hundreds of the shapes of the cell. We can have blood cells, epithelial cells, muscle cells, neural cells, lots of shapes, okay? And each cell has its own characteristics, size, structure, function in organism. And each one of these types of cells present subcategories when forming tissues, okay? So we have, for example, the epithelial cells, which are the ones we are, let's say, more interested in simulation on when we are doing tissues. Okay? So for the epithelial cells, we have this also subcategories to where the cells can be squamous, cuboidal, columnar, bunch of types of arrangements for the cells. And most of these structures can be modeled in CC3D. Okay, if you use proper plugins and steppables accordingly. Let's start with a simple simulation. Okay, this is the roadmap for the exercise. All the exercises are in the student materials demo codes folder. You can download if you want, but you can code it now if you want. I will pass the slides one by one here, saying what you have to do. But I will, at the end, I will show my code in case you don't have completed the simulation. I will doing the code right behind this screen behind the screen you are seeing now. Okay, let's start then for the first step as you saw yesterday. Let's start to edit with a new project. Okay, you started a new project. You go to the main page of the project, put a name on it. You name it the name if you want. I put a modular to cell shape. And you can choose the directory you want to put it. I will save it in a new place here, okay? And should choose also the Python and XML files together here as a simulation type. Next, you go to I have a bunch of screens here. You go to the next, sorry, I forgot to. You go to the general properties simulations. You have to define the grid there to change from 256, that is the default value, to 100. You have to choose a rectangular slab to start the simulations, and you go to the next page. The next page, you're gonna introduce the object of your simulation, the cell. So you choose the put a name like TestCell for the object. Click Add. And the cell will be included in the specification table. And then you go to the next page, where you have to choose the plugins that will give the cells the properties and behaviors you want to analyze it. So you are going to choose these 5 features here: contact adhesion, volume flex, surface flex, length constraint, and center of mass. By default, the cell neighbors come clicked, but you can unclick them because you don't need the cell neighbor right now. Okay? So let's continue. After you mark these boxes, go to next. And the next window is diffusion fields configuration. You don't have any. So ignore it, go next to the next page. And you have the contact and internal contact plugins. For now, we have only the contact energy matrix, the left table here. You set the neighbor order to 4. The default number, I think it's 2, but put it to 4. Okay? So you go to the next again, and your configuration is finished. Clicked Finish, and when you clicked Finish, this is what you saw in your tweet. The name of your project appears in the left panel. So what we're going to do now is to analyze these files. When you click in this name of the file, right-click in the name of the file, the 3 files appears. Let's see what each one does. The first one is the main Python file. It's a simple file that calls the user-defined structures and functions from the Steppable, from the last file you have in that list. Okay, this is generated by TwoEdit itself. The second one is the XML file. In the XML file is the file which call every plugins that you have loaded in that page of the wizard from behaviors and properties, and where you define and you set the parameters for the cells. You have here the pods part of the XML. You have the cell definitions, the test cell type, the only one you have, besides the medium, of course. You have the plugin volume, the plugin surface, the plugin center of mass, the plugin contact, and the plugin length constraint, and the UniformInitializer that we have chosen up as a rectangular slab. Okay? And the third one is the Steppable. The Steppable is a particular file where you write everything that you want that CompuCell does. I mean, every extra calculation you want to CompuCell to make, to alter, to interact with some cells, this is the place where you put it. Everything that is not in plugins must be included here. Okay? So now we are ready to run the simulation as is. Okay, you go to, as you already know, you right-click in the name of the project and open it in the player and see what happens. Of course, there is an alternative way to start the simulation by clicking the CC3D logo and open the player by its outside, from outside, and run the simulation, open the CC3D file from there. Okay, but this is now it's easier way. It's just open the player through the drop-down menu here, from the drop-down menu. Okay, you have the player. You already know that you have 4 buttons in the player. The plays the simulation, the step button, the pause button, and the stop button. Yeah. When you run the simulation, probably you are going to see something like that. Your simulation starts with a bunch of squared cells, and with time, the cells start to rearrange and ending in a rounded shape. But now let's do the following. Let's pay attention to a particular cell. Okay? Because we have lots of things happening here because all the plugins we included are functional. They are activated and work at the same time. This we are going to see now how each plugin works in a single cell to analyze it alone. Let's go there. Then we have to modify your code a little bit. You go to you can continue with the same code. We are going to modify it according with this roadmap here, but let's go step by step. So go to the XML file in the folder and go to UniformInitializer, which is the last part of the XML file. And there is a region, how to say a region here, a region part of the steppable where you define the size of the working space. This is defined by box min and box max. Box min says to the code where you are put the lower left corner of your simulation, of your working space, and box max say to the code where is the upper right corner of your region, your working space. So when I put 2020, it starts at 2020 here in the X and Y, and 88 is this point. 88 is this point. The next 3 space is when you have more than one cell. 0 is the space between the cells. Width is the width of each cell, the square of side 7, for example. And types means that which cell type must be included in this region we define in box min and box max. We are going to change this region now to these values here. We are going to change box min to 4040 and box max to 66. I mean, we are shrinking the square region of work. Now, instead of a square of side 60, we have a square of side 20 as a region of work. Also, we are going to change the width to 20 to say that we have only one cell fitting there. Remember, our box, our region of work, the space of work is a square of size 20. We are saying that the width of the cell is 20, so just one cell fits in that. Okay? So hit the save button and play the simulation. You must have got something like that. The cell starts a square, a single cell, and shrinks to a small undeformed shape, a kind of elongated, and the cell wanders around the space of the grid. Yes, you should have only one cell wandering about around the grid, moving around. Okay, good. Let's go on. Why this happens? I mean, first of all, if you don't see these intermediate steps from the initial step, from the initial stage to the final stage, you can stop the simulation, restart and going step by step, then you can see the decreasing of the cell size. Okay, but this happens why? Because all the plugins are active, like I said before. There is a competition between volume plugin, surface plugin, and length plugin. Everyone is working together here. So let's try to analyze one by turning off some of the plugins and analyze the effect of the one which is still on. Okay. Okay, but before going there, let's analyze the structure of the plugins. So we have 4 plugins here: the contact, the volume, the surface, and the length. Okay. Every single plugin has controls of cell properties, like volume, surface area, and length. These are the constraint plugins, volume, surface plugin. The contact energy is a kind of different. It's not falls in that category of plugins. But this one we can control according with this expression here. See? The way it works. Everyone works in this way. The energy of the plugin is introduced in the simulation through this expression here. We have a factor, lambda, which I call here lambda property, and a term which is the property value minus the target value square. What does that mean? Property value is the actual value of the property. I mean, the cell during the simulation in some Monte Carlo step, if you stop the simulation, you go to the screen, you count the pixels, they have that quantity of volume or surface or perimeter, whatever. This is the actual value. But the cell has a target value, which is a property of the cell. I mean, is an attribute of the cell who doesn't change. I mean, the cell always try to reach this value when he make some site pixel copy attempts. So if this term property value minus target value increases, the energy increases. So there is a penalty for that. And this is it's changing even if the property value is below the target value, doesn't need to go up. Which matters is the difference. If the difference is big, even if it's negative, negative is squared, it's positive, then energy is increased. So it is a penalty, and this copy is unfavored for the pixel copy attempt. Okay, so all the copies that bring the actual value, the property value close to the target are favored, and the others are unfavored. Okay, all the three plugins work in this way. Let's go on and analyze a little bit more. So here's how it works. See, this is the curve of the function of a parabola with the center, with the minimum in the target value. In this figure here, I draw only the volume plugin, but all the others works in the same time. The same time, no, same way, sorry. So we have the actual volume, the property value, V, S, and L, and the target values, VT, ST, and LT. Also, and the parameter in front of each expression, the lambda constraint, tells how much the cell resists to change its shape. Because the bigger the lambda, the higher the contribution to the energy. So if the contribution to the energy is higher, we have less accepted values for the pixel copy attempts. Okay? Okay, let's explore the effect of the volume constant. You can continue with the same model, the same code you have. Okay? So this is the roadmap, but again, I'm going to one step by step. And now we go again to the CC3D XML script file. And we are going to change to the plugin surface. We are going to change the lambda surface and set to 0. Put this to 0, we turn off the contribution to energy because the multiplier factor here is 0. So it doesn't do anything to energy of the system. Okay, we are turning off the plugin. Also, we are going to set it to 0, the length plugin, by setting the lambda length to 0. Remember, again, we are put to 0 this quantity here, so no contribution to energy at all. After this simple change, you save it and open in player and play the simulation. Now you have these things. So if you have to go step by step. What happened, the difference between this situation now and the previous one when we ran with all the plugins active is that the cell here is much more round, more symmetrical. Remember the other one is elongated because the length plugin was active. So the length plugin gives you how much the cell must be elongated. Now it's 0, so no elongation, the cell stands round, as much as closer as it can from a circle here because of the surface tension. Okay? Good. These are very simple exercise, but it's good to see what the effect of each plugin. Okay, now let's change. Now, this is, I forgot to show you, this is a comparison before and now. Né? Before we have this uh, wiggly and elongated shape, and now we have more rounded shape and smooth shape. The question that still continues, why the volume shrinks? You start with this big square and end up with a small circle. That's easy because we have put as initial condition in the XML file, remember? We have put the width as 20. That means that our cell start with 400 pixels. But when we define the volume plugin, we put the target volume as 50. So that's why the cell shrinks from 400 to around 50. Okay? So we can fix that by go to the XML file again and change the target volume in the volume plugin from 50 to 400. And play it again. You should have now this behavior. The cell doesn't shrink anymore. The volume now is preserved. The shape changes because of the contact energy with the medium. But since we don't have any surface plugin working and any length plugin or activated too, the cell tends to be a circle. If it were in 3D, we'll have a sphere here. Yeah? So let's move on. If we can play a little bit with the target volumes to see what happens. For example, put target 30, 400, and 1,000. Let's give you 2 minutes to try that to see what happens. See if you can reproduce these figures here. Oh yes, you have to change the lambda length, not lambda volume. You can also try set VT to 0, and the cell must disappear. So this is a particular way to kill a cell in a simulation. Put its target volume to 0, and the cell naturally will disappear during the simulation. Well, I don't. Well, it could be apoptosis, but it can be provoked for something else. And maybe if you have some chemical interaction saying that the cell should die, then you can decrease its volume slowly, for example, by not set the target volume to 0, but change the target volume to 0 step by step, for example. You can do that, yes. And there is another, yes, you can, but you have to use a different plugin now. If you try, for example, target smaller than 30, 20, for example, even so the cell will disappear. This happens because we can talk, I think we will talk about this later in another lecture, but when you decrease too much the target volume, and doesn't change anything else, for example, the lambda volume, the volume energy isn't enough to keep the cell because there are the contact terms with interaction between the cell and the medium, and this term could be more predominant against the volume, and the cells end up by disappearing. It's a competition, no? You have to remember that the energy is a sum of many terms, and all the terms are competing during the simulation. You have to adjust to have a physical and a biological acceptable uh, configuration. Okay. Now let's explore to what happens if you change the lambda volume. Okay. Look, for example, go again to the volume plugin and change the lambda volume to 1,000 and put the simulation to run. Okay. Actually, sorry. First, you put the target volume to 1,000 and keep the volume to 2. Now you have your cell growing because from 400 to 1,000 pixels. Okay. Now, how do you change how do you see the fate of the lambda volume? Let's see. Let's put it to 10, 100, and put it to 100, save the simulation, and put it to run. What's going to happen? What do you expect? That's what happened. The cells grows, but the membrane fluctuations are much smaller. I mean, the cell is not round anymore, not circular. Why? Because, as I told you before, high strong constant strain, once the cell reaches its target value, it's difficult to change it. Remember the behavior of the function, the parabola? Here it is. So this is what happens. For the low lambda volume, you have a very wide parabola, the blue one. So you have both curves here. The red one is with high lambda volume, and the blue one is the low lambda volume. So when it's much more difficult to change to accept the flips when you increase the lambda volume, because the penalty energy grows up if you have high values for that. Okay? So the cell freezes, doesn't change anymore. Actually, it changed, but much, much slower. So let's analyze a little bit what is going on here. If you want to, actually, this is another way to freeze a cells in simulations. You can freeze by changing a particular lambda volume for a particular cell. Okay? why is a critical value? Now we have to analyze this. Look, there is also another parameter in the simulation that acts in the energy, actually acts in the probability of acceptance in the pixel copy attempt. Is the membrane fluctuation amplitude, which is called temperature in the POTS part of the XML file. Huh? The constraint, when you change the constant, the lambda property, you are altering the relative value with the temperature using the simulation. Let's understand this graph here. This graph shows the variation, the probability of acceptance of a pixel copy attempt when the energy decreases, delta H is negative here, the energy decrease, the probability of the change the pixel is always 1. When the delta H, the variation, is importing increasing in the energy of the system, the probability is calculated according to this expression here, the Boltzmann's expression. It involves a ratio here between delta H and T, the temperature. Okay? So delta H is a sum of two terms, the contact energy and the volume energy. If you increase the fluctuation amplitude by 100, the lambda volume by to 100, you are increasing the energy term here and increase the numerator of this fraction. If you increase the numerator of this fraction, you increase the result. If you increase the result, you decrease the function e elevated to minus a big number. So this result is small. So the probability to change is small. And that's why the cell freezes. Since we are not change anything with the contact energy here, this ratio increase and the probability decrease of change, and the cell freeze. Okay, this is how the machinery of the POTS model works with the both probability. Let's move on. Okay. So in the current simulation, we have 10 as the value for the temperature. We can change it now and here and setting the temperature to 100. I mean, it's like, okay, we are increasing both energy, volume energy contribution and temperature by the same amount of 10, multiplied by 10 both. What do you expect of that? Do you expect that simulation comes back to the previous one when we have 2 and 10? Let's see. Let's run. Try it. Yes, the connect will be faster. But will the cell be rounded again? Be very smooth? This is what happens. The first simulation, we have 110. We have this kind of thing. And now we have 100 and 100. That's what we got. It's very different. The cells start to be very hot. Why? Let's go back to the analyze the energy terms. We have two terms competing, volume and contact energy. The contact energy are always constant because we are not changing anything with the between the cell and the medium, with the black stuff behind the cell. But when we increase the temperature and the lambda volume, you are decreasing the relative contribution of the contact energy, actually. Remember, you have two terms. When you increase the temperature to 100, now you are dividing the contact energy by 10 times more than the volume energy. So the contribution, the importance of the volume energy to the energy, the total energy is much bigger. So to keep the cell smooth, which is the role of the contact energy, is no longer a priority because the contribution is much small, 10 times smaller than before. So the volume is more important now. And that's why the cell keeps much more wiggly, more rough in the surface. Okay. Now what happens if you go from the temperature for 100 to 1? It's easy to realize that. The cell freezes. The cell also, with time, the cell gets a rounded shape, approximately rounded shape, is the left panel here, but freeze. Because again, it reached its volume, and since the temperature is too small, the probability of acceptance decreased too much. Is just look at the graph here again. Now the temperature 1 is the blue, and the black is the temperature 100. If you have 100, the temperature goes up. Sorry, the acceptance increase. If it goes to 1, the acceptance decrease. Awesome. Okay, this is the competition. So when you are doing a simulation, you have to be careful when you start to change only one parameter and doesn't look to the others that may influence the simulation, such as temperatures, for example. Okay? Okay, let's change to the surface plugin. We have to go faster a little bit now. Okay, the surface plugin is almost very similar. We have the same shape, and the surface is counted. See, you don't have surface here because we are in a 2D system. So surface now is perimeter, and the surface here is measured in units of cell size. So here we have a 1 pixel volume cell, and it has 4 sides. So the surface is 4. For a volume of 4 pixels, we have 8 sides and so on. Okay, so we can write a approximated relationship between volume and surface like that in a 2D square. The surface is approximated 4 times the square root of the volume target. Okay? So let's use this expression in the simulation. So now you change again the code. go back to your XML, go back to the previous values, temperature equals to 10, lambda volume equals to 10, volume target equals to 1,000, set the contact energy between medium and the cell equals to 0, okay? And let's use this relationship to set the target surface for the plugin. But remember now we had put it to 0 before. Now you have to set back to 10 in the lambda surface. And target volume is 126. It's the square root of 1,000. It's approximately 32, 33. Times 4 is 126. This is the value you put there. Okay, save the simulation and run. It's what you should see. The cell is a square and doesn't change. Okay, it keeps squarish, doesn't move, doesn't change at all. Why? Because we have competition between both plugins. The volume, which keeps the cell in 1,000 pixels, and the surface that keeps the surface in 126. And there is no influence of the contact energy. We have put it to 0. Only these two are actually working here. So the CompuCell tries to satisfy both plugins, the surface and the volume. Okay? Let's try with different values of surface plugin. Let's change it. I will give you some minutes to use these values. 60, well, 126 you have, 135, 300, 600, and 2,000. See if you get these shapes here. For small values than 126, actually, there is no much influence of the surface plugin because of the volume plugin, which keeps the volume in 1,000. So we cannot go down of 126. But if you increase above 126, the cell shape starts to round up. If you go too much above, the cell starts to create structures like fingers because it tries to increase its surface area. Even more, if it's 600 here, the cells start to break apart because the plugin is trying to be satisfied by the code. So if you have a detached part of the cell, the surface area of this small part here is bigger than if this part was stick to the big blob. And if you put 2,000, the cell disassembled, it's completely fragmented. Okay, you have to adjust your plugins, your targets to have the more biological shape according to the system you are trying to reproduce. Okay? I'm going ahead. Everybody got that? Yes, it looks like fireworks. Yeah. The final one is the length constraint. The length, again, the same shape, the same structure of the function. And before we explore, let's change again the XML. And now we are going to turn off the surface and turn back the contact energy. I mean, that's what we have to do. We have T equals to 100, so, 10, lambda volume 10, volume target 1000, lambda surface set to 0 again, and the contact energy between medium and test cell go back to 100, 10 again. Go to the XML, locate the plugin part, and now we are going to use this relationship between length target and volume target. Remember, if you the length, if you treat the cell at the beginning as a square of side 20, okay, you have 1,000 of pixels. The square of 1,000 is 32. So this should be the length of the cell. This is approximated function. So this is the value we are going to put in the target length, 32. And for the lambda length, we are going to set to 5. So this value is approximately 2D square lattice, like that. Just to justify the function, the approximated function, we are going to use that. Now, make the change, save the code, and run. For L equals to 32, you have this rounded shape because we start with the assumption that the 32 is the size of an elongated cell this way. Now you can change the elongation, change the target value for that. For example, if you set to 40, you elongate a little bit the cell. If you go up, 60 is you have some kind of ellipsoid here, not very much similar. With 80, you have a bastonet, like a bacterial cell. You can create a bacterial cell like that, elongated to 80. So the higher the target length, the more elongate the cell. Okay? Yes, length is if you have the cell in a shape, if you can measure it along the x axis. Yeah. If you put values smaller than 32, what do you expect? Since there is competition because we still have the volume constraint active, nothing very, there is not much changing in the elongation, but in the whole shape of the cell. The cell freeze because there is no way to because of the volume constant, there is no way to shrink the cell anymore. The 1,000 pixels of volume prevents the change the elongation to a small number. So the cell freezes. There is no way to satisfy the plugin. If you increase the lambda volume to 500, the cells start uh, to become wiggly again, because again, this is looking back to the competition between energy terms in the probability of acceptance. That's what happened. The cells try to elongate, but the probability is too small to accept the change. So I think with those 5 examples, you can I could show you a good you can have a good idea how you can manipulate the constraints values, the parameters of the plugins to shape your cell the way you want for your biological experiment or simulation. Okay, so I think you have to be careful to to with the choice of your parameters, because sometimes if you use unrealistic values, you can have unrealistic cells, and the simulation can be frozen with those kind of values. Okay, so I finish here, and thanks for your attention. If you have questions. For lattice, the shape is always the same. Yes, that's true. Because of the volume. That value of 32 that we put in the beginning were the value, specific value for the volume of 1,000 pixels. So if you go lower than that value, it cannot arrange itself. If you decrease the target volume, then you can use small values for the target length.